So today we shall see Maximum Modulus Principle, its different versions and examples based on this Maximum Modulus Principle. See, in the last video, Identity Theorem 3, there were two mistakes, and those mistakes were rectified in the comment written below that video. The second comment that was that was asked by Shreya. She has told me that there is some mistake, and thank you. So let us go for this different versions of maximum modulus principle or maximum modulus theorem. Let us see the first statement. If f is analytic in a region G and A is a point in G which satisfies the condition mode of fa greater than or equal to mode of fz for all z in G, then f is a constant function. G is a region not necessarily bounded. F is analytic on G and A is a point in G such that mode of fa is greater than or equal to mode of fz, then f is a constant function. Means if for an analytic function f on a region G, if the function mode f has maximum in G, then f is a constant function. This is another version of the maximum modulus theorem or maximum modulus principle. Let G be a bounded open set in C, and suppose that f is continuous on the closure of G and f is analytic in the region G. Then the theorem says that the supremum of mode of f over the closure of G is same as the supremum of mode of f over the boundary of G. Here we can write maximum. Why? Because f is continuous on the closure of G, so mode f is also continuous on the closure of G, and because G is bounded, G closure is a compact set, and continuous function on compact set attains its extreme values, and therefore in place of supremum we can write here maximum. So again I am saying here G is given to be bounded. That is important part here. In the first one, G is not necessarily bounded, and in the second theorem one can see that this G is not necessarily connected. Means it is not necessarily a region, it is just a bounded open set, right? Now if we combine these two, then we get this statement. Let G be a bounded region. Let f be continuous on the closure of G and let f be analytic on G. Again, let G be a bounded region. Means G is a bounded open connected set. F is given to be continuous on the closure of G. F is analytic on G. So if we combine, what we are going to get, if f is non-constant, then mode f has maximum only on the boundary but never in the interior. Again, G is a bounded region. F is continuous on the closure of G. F is analytic on G. If f is non-constant, then mode f has maximum on the boundary of G only but never in the interior, because if it has mode f has maximum in the interior, then by the first theorem it will become a constant function, and because G closure is compact, maximum is going to be attained, so it is to be attained on the boundary only. So as I said, in the first theorem we are not assuming that G is bounded, not assuming, yeah, and in the second theorem we require that G to be bounded. So in the second theorem, if we drop the boundedness of G, then it is not true. Means in place of G, in place of, if we drop this boundedness, then the conclusion may not hold. So we give that example. The example which we are going to show is this. So what we need to do, we need to find out an unbounded open set G. such that f is continuous on the closure of G, f is analytic on G, but these two numbers. So now we should not write maximum, now we should write supremum. See, because here in this theorem G is bounded, so G closure is bounded. So whether we write supremum or maximum, they are one and the same. But when we want to give an example, means the conclusion may not hold when G is unbounded, the maximum should be replaced by supremum. So we need to find out an unbounded open set G such that, and a function f which is continuous on the closure of G, which is analytic in G, but supremum of mode of fz, z in the closure of G, is not necessarily same as supremum of mode of fz, z is in the boundary of G. So now we give that example. So let us take G to be the collection of all complex numbers x plus iy such that the imaginary part of z that lies between minus pi by 2 and pi by 2. So in fact it's an open strip parallel to x-axis, and we take f of z to be exponential of exponential z. Because exponential is an entire function, so composition is also an entire function, and therefore the function f is continuous on the whole complex plane, f is analytic on the whole complex plane, and therefore in particular f is continuous on the closure of G and f is analytic on G, right? Okay, now let us take any point z from the boundary of G. What is the boundary of G? The boundary of G contains precisely the points of the form x plus minus I pi by 2, where x is a real number. That is the boundary. So if we take any z from the boundary of G, what we get, z is of the form x plus minus I pi by 2. We are going to evaluate mode of f at these points. So what we get, mode of fz equals mode of exponential e power x into e power plus minus I pi by 2, that is equal to mode of exponential of plus minus I e power x. Why? Because e power plus minus I pi by 2 is plus or minus I, and it is known to us that mode of e power I theta for real theta, mode of e power I theta is 1. So mode of fz is 1. For which z? For every z on the boundary. Therefore supremum of mode f over the boundary is 1. Okay. Now one can see that this function is unbounded on G. How? Because if we take x tends to infinity through the real numbers, means x is tending to infinity through the real numbers, what we get, f of x is tending to infinity. That can be verified easily. This f of x will be a exponential of exponential x, and as x is tending to infinity, then f of x will tend to infinity. So supremum of mode f over the closure of G will be infinity, whereas the supremum of mode f over the boundary of G is 1. Therefore we have shown that these two numbers are not equal. Why we are not getting that equal? Because we have dropped the condition that G is bounded, right? So now we shall see some examples, and we also see that in the second example, it is G is not necessarily connected. In the first one it should be connected, na? G. Let us see some examples based on this maximum modulus principle. So let G be a bounded region. Let f be a function which is continuous on the closure of G, and let f be analytic and non-constant on G. This is given. If f of z not equal to 0 for any z in the closure of G, then we want to show that mode of f has minimum in the closure of G, and this minimum will be attained only on the boundary of G. Again, G is a bounded region, f is continuous on the closure of G, f is analytic on G, f is non-constant. If f is nowhere 0 on the closure of G, then we want to show that mode of f has minimum value on the closure of G, but that minimum is going to occur only on the boundary, right, but never in the interior. So see, uh, we start, we start with the hypothesis, and before going for the solution, this statement, it is also called minimum modulus principle, because we are talking of the minimum of mode of f. So since f of z not equal to 0 for any z in G closure, and f is also given to be continuous on the closure of G, the function 1 upon f is continuous on the closure of G, and it is also known to us that f is analytic on G and f is nowhere 0 on G, and therefore the function 1 upon f is also analytic on the region G. And because f is also given to be non-constant, the function 1 upon f is non-constant. So now what we have, 1 upon f is continuous on the closure of a bounded region G, 1 upon f is analytic on the region G, and 1 upon f is non-constant. Therefore, by maximum modulus principle, the function mode of 1 upon f has maximum value which occurs only on the boundary of G but never in the interior. So suppose that the maximum value of 1 upon f, mode of 1 upon f, is attained at the point z naught of the boundary of G, then one can show easily that the function mode f has minimum value at that point. And you can also prove the converse. That means if mode of f has the minimum value at a point say z naught, then mode of 1 upon f we will have the maximum value at that point. So what we have shown, therefore we have shown that mode of f has minimum value only on the boundary of G, and in fact that is what we are requiring, that is what we want to show, mode of f as minimum value in the closure of G, but that is not going to occur in the interior, it is going to occur only on the boundary. But in this case, if we drop the condition, the first condition, f is nowhere 0 on G closure, if we drop the condition, then it is not necessarily true. Means mode f may have minimum at a point which is not on the boundary. So we give that example. We define f from the closure of the unit open unit ball to C by f of z equal to z. One can see that this function is 0 at a point 0, so the condition f of z not equal to 0 for any z in G closure is not satisfied. Then one can see that the mode of f has minimum value in the interior of B01 closure, namely at a point 0, right? Therefore this condition f of z not equal to 0 for any z in the closure of G is necessary. Let us go for the third example. Let G be a bounded region. Suppose that f is continuous on the closure of G and analytic on G. If there exists a constant C greater than 0 such that mode of f equal to C for every z, mode of fz equal to C for every z on the boundary of G, then we want to show that either f is a constant function or f has a 0 in G. Again, G is a bounded region, f is continuous on the closure of G, f is analytic on G, and for some constant C positive, mod of fz equal to c for every z in the boundary of G. Then we want to show that either f is a constant function or f has a 0 in G. So now we have to show either the first statement holds, namely f is a constant function, or f has a 0 in G. So we are going to assume that one of these two statements is not true, and then we are going to show the other one remains true. So we assume that f has no 0. See, what is the negation of the statement f has a 0 in G? The negation of the statement is f has no 0 in G. So suppose that f has no 0 in G, and it is also known to us that mod of fz equal to c for every z on the boundary of G. So f is also non-zero on the boundary of G. That means f is nowhere 0 on the closure of G. Right, then by the last example, by minimum modulus principle, mod of f has minimum on the boundary of G. And it is also known, see, we are not given that f is constant. I mean, we have to show f is a constant function. So mod of f has a minimum value on the boundary of G by minimum modulus principle. And by maximum modulus principle, mod of f has maximum on the boundary of G. Right. So we have a function mod f whose maximum is attained on the boundary, minimum is also attained on the boundary, and therefore mod of and on the boundary, mod of fz is c for every z on the boundary, and therefore it follows that mod of fz equal to c for every z in G, or in fact G closure. Right. So what we have shown, mod of fz equal to c for every z in G closure. So in particular, mod of fz equal to c for all z in G. We know that G is a region, and it is known to us that if G is a region, f is analytic on G, and if mod f is constant on G, then f is a constant function. So by that result, since mod f is constant on the region G, f is also a constant function. That means what we have shown that f is a constant function on the region G. What do we want to show? F is constant on the closure of G. So what we do, let us take any point A from the boundary of G. Then we get a sequence Zn from G which is converging to A. Because f is continuous, f of Zn will converge to f of A. But it is known to us that the values of f of Zn, they are all one and the same. Therefore limit also has the same value, and so continuity of f on G closure implies that the function f is constant on the closure of G. And thus we have shown that if we are given a function f defined on the closure of a bounded region G, f is analytic on G, and if mod f is constant on the boundary of G, then either f is a constant function or f has a 0 in G. See, if here c is 0, then obviously mod of fz is 0 for all z on the boundary, but then by maximum modulus principle, f will turn out to be the 0 function. So I've dropped the case that c equal to 0. Let us go for the next example. Let f be analytic on the disk B0R, and for 0 less than or equal to small r less than capital R, we define AR to be maximum of real part of fz. Z has modulus R. We want to show that if f is non-constant, then AR is a strictly increasing function of R. See, this AR is going to depend on R. If we change R, then this is going to be changed. So AR is a function. In fact, it's a function defined on close 0 to open capital R. So we have to show that AR is a strictly increasing function provided f is analytic and non-constant on the disk B0 R. Okay, so in proving this we shall use a function. We shall introduce a new function. So define g from B0R to C by g of z equal to exponential f of z. Because f is analytic, exponential is an entire function, g is an analytic function. Okay, and again because f is a non-constant function, g is a non-constant function. Let us take any two r1 and r2 such that small r1 less than small r2 less than capital R, and this r1 is greater than or equal to 0. Because the function g is continuous, on B0 R1 closure g is analytic, so by maximum modulus principle we get some z1 on the boundary of B0 R1 closure. So mode of z1 has modulus R1 such that mode of gz1 is same as maximum of mode of gz mode of z less than or equal to R1. And again by maximum modulus principle, this maximum is same as maximum taken over the boundary. By the same way, using maximum modulus principle, we get some z2 with mode of z2 equal to R2 such that mode of gz2 equal to maximum of mode of gz mode of z has modulus less than or equal to R2. And again by maximum modulus principle, this maximum taken over the closed ball is same as the maximum taken over the boundary. Okay, now obviously B0R1 closure is subset of B0R2 closure, therefore mode of gz1 is less than or equal to mode of gz2. Can they be equal? No. Why? Because this function g is analytic, or in fact continuous. This function g is analytic on B0R2 and g is non-constant, so we are not going to get any point from the interior where mode g is maximum. So mode of gz1 cannot be same as mode of gz2, and already we have seen that mode of gz1 is less than or equal to mode of gz2, and so what we get mode of gz1 is less than mode of gz2. Okay, we note that mode of gz is nothing but exponential of real part of f of z, and so maximum of mode of gz, maximum taken over mode of z equal to r, that is same as maximum of exponential of real part of fz mode of z equal to r. In fact this maximum will be attained say at a point exponential real part of f of z naught, right? And because it is known to us that exponential is an increasing function, and because mode of gz1 is less than mode of gz2, it follows that AR1 is less than AR2. Thoda sa, I mean, one has to work here. See, you call mode of gz2 na, it is attained, but mode of gz2 is what? Exponential of real part of f of z2, and here it is same as exponential of real part of f of z1, and because exponential is an increasing function, or one may apply log also there, so we are going to get maximum of real part of fz taken over mod of z equal to r1 is less than maximum of real part of fz, and that supremum taken over r2, or mod of z equal to r2. So that finishes the proof. In fact, it is roughly the same proof what we have seen here. So this you may do. Let f be a non-constant entire function. For r positive, let us take m of r to be supremum of mod of fz, mod of z less than or equal to r. We may also write here maximum, because it's a compact set, mod f is continuous, so supremum will be attained. Then we need to show that m is a strictly increasing function, because f is given to be non-constant. Is m continuous? That you need to check it. So will m be continuous? The proof of the proof of the fact that m is strictly increasing, it is roughly the same one. You need to use maximum modulus principle. So let us go for next example. Let f be an entire function such that f of z is real for every z satisfying mod of z equal to 1. Then we need to show that f is a constant map. So given any entire function f which is real valued for z satisfying mod of z equal to 1, then f has to be a constant map. So because f is an entire map, f is a complex valued function, so f has the form u plus iv. Okay, so if we take any z equals x plus iy with mod of z equal to 1, then by hypothesis f of z is uxy. Why? Because it is given that f of z is real for every z satisfying mod of z equal to 1. So we have taken any z equals x plus iy which satisfies mod of z equal to 1. So by hypothesis f of z is uxy. Now we define two functions. So the first one is g equals e power if, and we define h to be e power minus if. Then both the functions g and h are entire functions, because composition of entire functions is an entire function. Now we take any z equals x plus iy satisfying mod of z equal to 1. Then what will be mod of gz? Mod of gz is same as mod of e power iuxy, because it is known to us that f of z has the form uxy for every x plus iy, z equals x plus iy satisfying mod of z equal to 1. And so what we have shown? We have shown that mod of gz equal to 1 for every z having modulus 1. So by maximum modulus principle, what we are going to get? Mod of gz is less than or equal to 1 for every z having modulus less than or equal to 1. Now again take any z equal to x plus iy having modulus less than or equal to 1. Right. Then e power minus vxy, that is same as e power I uxy plus ivxy. See, because mod of e power I uxy is 1, right? So e power minus vxy is same as mod of e power I uxy plus ivxy, but this is same as mod of gz, and it is known to us that if we take any z with mod of z less than or equal to 1, then mod of gz is less than or equal to 1. So what we have? E power minus vxy is less than or equal to 1, and this implies that vxy has to be non-negative. And just forget this. What we have shown, e power minus vxy is less than or equal to 1, and therefore vxy is greater than or equal to 0. Provided what? Provided mod of x plus iy is less than or equal to 1. Now if we do the similar analysis to the function f, then we are going to get vxy less than or equal to 0 for every z equal to x plus y satisfying mod of x plus iy less than or equal to 1. So here we have shown that vxy is greater than or equal to 0 for every x plus iy which has modulus less than or equal to 1, and here we have shown that vxy is less than or equal to 0 for all such x plus iy. So it turns out that vxy equal to 0 for every x plus iy which satisfies the condition mod of x plus iy less than or equal to 1. So on the closed unit disk we have shown that f is real valued. So in particular f is real valued on the open unit disk D, and yes, on the f is, and it is known to us that f is analytic. So f is analytic on the domain D. Here D is open unit disk. We have shown f is real valued, and it is known to us that if f is analytic and real valued on a region or a domain D, then f is a constant function, and therefore f is a constant function. Now f is an entire function and f is constant on the open unit disk D. So now you need to apply identity theorem to get the conclusion. Now that I am leaving because we have already discussed identity theorem, so you should be able to prove that f is constant on the whole complex plane. So this is over. Let us go for another interesting example. Let p of z equal to z power n plus a n minus 1 z power n minus 1 plus up to a naught, where a naught, a1 up to a n minus 1 are complex numbers, and we take another polynomial qz to be 1 plus a n minus 1 z up to a0 z power n. It is given that mod of pz is less than or equal to 1 for all z in C, satisfying mod of z less than or equal to 1. Then we have to determine which of the following statements are true. The first statement is mod of qz is less than or equal to 1 for all z satisfying mod of z less than or equal to 1. Q is a constant polynomial. P of z has the form z power n for all z in C. P is a constant polynomial. So we are given two polynomials pz and qz with the condition that mod of pz is less than or equal to 1 on the closed unit ball. Then which of the following four statements are true? So more than one statements are true. Let us see which of these statements are true. So as I said, both p and q are polynomials, so they are entire functions. Now let us write f infinity for f infinity, or let f infinity denote the supremum of mod of fz, where supremum is taken over the closed unit ball. Okay, then we have the supremum of q taken over the closed unit ball. It is this one. This is what we have introduced, and by maximum modulus principle this supremum is same as supremum taken over the boundary. As I said, this is because of maximum modulus principle, and that is same as supremum of 1 plus a n minus 1 z up to a0 z power n. Q we are given here. Q has this form, but because mod of z is 1, 1 upon mod z is also 1, so we may replace z here by 1 upon z. That is what we have done. Again, why? Because mod of z is 1 if and only if 1 upon z, mod of 1 upon z is 1. So z can be replaced by mod of 1 by z, and this simplification, if we take 1 upon z power n outside mod, then we are going to get 1 upon mod z power n, then mod of z power n plus a n minus 1 z power n minus 1 up to a naught, where this supremum is taken over mod z equal to 1, but mod z has modulus 1, so this will go away, na? Because this will become 1. Now this term is what? This term is nothing but p of z. No, p of z we are given. P of z is z power n plus a n minus 1, z power n minus 1 up to a naught. So this is nothing but the polynomial pz, and this is its supremum. And what is known to us? Mode of pz is less than or equal to 1 for every z in C satisfying mode of z less than or equal to 1. So this supremum is less than or equal to 1. So we have mode of the supremum is less than or equal to 1, but we know that supremum of p is same as supremum of q. Therefore this supremum is also less than or equal to 1. What does that mean? Mode of qz is less than or equal to 1 for all z satisfying mode of z less than or equal to 1. And if you see the form of q of z is what? 1 plus a n minus 1 z up to a0 z power n. So what is q of 0? It is 1. So supremum of q over the closed unit ball is less than or equal to 1, and the value 1 is attained, and therefore supremum of q is 1. But now one can see that q is a analytic function on the closed unit ball. In fact, q is analytic on the open unit ball, q is continuous on the closure of the open unit ball, and mode of q has maximum in the interior because q of 0 equal to 1 we are getting. So by maximum modulus principle, q has to be the constant function. Again, q is continuous on the closure of the open unit ball, q is analytic on the open unit ball, and mode of q has maximum at the point 0, which is in the interior. So by maximum modulus principle, it follows that q is a constant function. So it's a constant polynomial, and that means a n minus 1 up to a naught, these all constants have to be 0. So q of z is 1. So if all these constants are 0, then what is the form of pz? Then form of pz is z power n, because all these a n minus 1 up to a naught are 0. So the first statement is true, the second statement is true, and the third statement is true, and the fourth statement is not true, right? So by maximum modulus principle, q is a constant function, so a0 equal to a1 up to a n minus 1, they are all 0, and thus p of z equal to z power n. So we stop here. If you have some suggestions or some comments, please write below the video. So I'll take care when I make the next video. Thank you.